All right, so yeah, welcome to the first GSG session for Math 230 and 231 over summer. If you guys don't know yet, my name is Steven, call me Steve, and I'll be your guided study group leader throughout the summer. All right, so I'll start off with a few announcements regarding GSG, and then we'll get into the lesson plan for today's session. So if you guys aren't aware, these sessions will be held every Thursday at 4 p.m. Eastern time. And for those of you guys attending in real time, if you could please type in your Penn State user ID in the chat box. So the ones with for me, it's SUS 676. So not your Penn State ID number, but yeah, perfect. All right. Okay, and I think that is it regarding the GSG logistics. And so I'll start off with the introduction to how I'm going to set up these GSG sessions. So normally what I do throughout the semester is I have a lesson plan covering all the important topics from lectures. So in this case, we'll be covering kind of the key concepts from Monday and Tuesday's lectures. And then from that, I'll be providing extra examples to practice on, basically. All right. And in terms of the schedule, it'll be very flexible. So if you guys want me to cover a certain concept, let's say from 12.1, instead of going through 12.3 and 12.4, just feel free to let me know. Either if you're attending real time, just let me know in the chat box. Feel free to unmute yourself if you wanna kind of just converse, or yeah, add a post on Piazza. Okay. All right, and I will try not to overlap too much with what has been covered during lectures and recitations. So any questions regarding GSG and any of that? All right, sounds good. All right, so for the lesson plan for today's session is gonna be covering 12.1 to 12.4. Where 12.1 is kind of like an introduction to kind of like the pre-calc or like the geometry of this introduction to R3 space. So yeah, let's start off with that. Let's see. Let me see if I can pull up a whiteboard. There you go. Okay. Give me a minute. All right, there. So 12.1. 12.1. So in yesterday's recitation for 12.1, you guys covered basically equations dealing with spheres, finding its center, finding its radius. So I won't be covering too much off of that unless you guys have any questions you want me to cover. All right. So give me a minute. So yeah. So for 12.1, I'll be focusing more towards representations of equations in R2 and in R3. All right, so let's start off with this equation right here. So let's say we're given an equation x squared plus y squared is equal to 9. Okay. And so let's say a given question says that graph this equation out. As Joe mentioned in Monday's lecture, you can't really do that without the context of the situation or the question. So in this case, you also have to specify whether you're trying to graph it out in the real Curtis space R2 or the XY plane, which is basically the XY plane, or graphing it out in R3. All right, which is, I guess you guys can consider it as space for now. All right, so in R2, as covered in lecture, this is basically gonna look something like a circle with a radius of 3, right? That's just based off this equation. But in R3, hold up, let me use the eraser. In R3, it is not going to look like that. All right, so any questions so far regarding the representation of x squared plus y squared in R2? No, perfect. All right. Let me see if you can see the chat box. I can't see the chat box right now. Give me a minute. All right. There's some technical difficulties. All right. Okay. Well, I guess yeah, we'll have to deal with this. So for R3, as mentioned in Monday's lecture, you want to start off by. I'm just going to start off by drawing out the axes. So for this class, for Math to 30, we'll follow the convention of following the right-hand rule. So, so basically you have X pointing outwards, and then you're gonna curl your right hand towards the y-axis, and the thumb basically points up to the z-axis, right? So we have something like this. So if you try to graph out x squared plus y squared, it's gonna look something like a circle of radius 3, all right? So yeah, that's not quite a great. I'm just trying to see if I can draw this better. Let's see, something like this, and then something like that. All right, so yeah, imagine that's in the XY plane with a circle with a radius of 3. Okay. All right, so now in regards to R3, since we have 3 degrees of freedom, imposing this one equation of x squared plus y squared does reduce the degree of freedom from 3 into 2. Now, the restriction that this equation doesn't have is that it doesn't specify points in z. So this circle can also be represented at z is equal to 1, at z is equal to 2, at z equals to 3, and basically any real value of z. So that is why it's gonna look something like a cylinder without a volume. Okay, so any questions so far? Okay, feel free to unmute yourself because I cannot seem to find the chat box when I'm using the whiteboard. Okay, so stop me if you have any questions. All right, so that is that for x squared plus y squared is equal to 9. So this basically represents a curve in space. Okay. All right, and whenever, another key concept is whenever you kind of enforce a new equation, you tend to lose a degree of freedom, as mentioned in class or in lecture. Okay. All right, so yeah, let me just start off with a new whiteboard. Okay. So another thing discussed in Monday's lecture is this idea of inequalities in space. So we do have kind of like a surface. So like as shown before, x squared plus y squared is equal to 9. In R3 is gonna look like a cylinder with no volume. Now, in order to provide kind of like solid regions in space, we basically deal with inequalities. So let's say we're given this inequality of, let me just clear this up. Let's say I'm dealing with the inequality of x squared plus y squared is going to be less than or equal to 64. Okay. And let's say we're going to specify this in R3. So the context of this is in R3 space. All right. So first of all, yes, I'm going to draw that out. So again, just going to draw out the axes, the coordinate axes of x, y, and z. And remember, right-hand rule for where your x and y's are supposed to be situated. Okay. So for x squared plus y squared is going to be less than or equal to 64. So first of all, whenever I'm trying to graph this out, I start off with kind of what the equation is going to look like. So this is, again, going to represent something like a cylinder. All right, this is going to be a cylinder with a radius of 8, right? And whenever it says less than or equal 64, you're basically trying to signify every point inside that restriction. So in this case, you basically, so if I were to draw out like extra cylinders right there, extra circles right there, which is just basically x squared plus y squared is equal to 64. Whenever you have a less than or equal to 64, it's every point inside of this diagram. Okay, so that is what basically an inequality represents in R3 space. Okay. So any questions so far? Okay, and then last one I'm gonna mention is, let's go over this example. So let's say we have, instead of x squared plus y squared, let's say we have x squared plus y squared plus z squared, which is going to be less than or equal to 64. All right, and let's say that is also greater than or equal to 1. And you're trying to represent that in R3 space. Yeah. So with these kind of questions, I start off by splitting the inequality into two different pieces. So let me start off with x squared plus y squared plus z squared is going to be greater than or equal to 1. Okay. So let me split it up into 2. All right. So let's see what this looks like first. So again, this graph is going to look something like a sphere. Right, and this is again based off what you guys have covered in lecture with the kind of like the distance formula and implementing that. So this is basically going to be a sphere with a center of 0, 0, and 0, because this is going to look something like x minus 0 squared plus y minus 0 squared plus z minus 0 squared, right? And that's going to be greater than or equal to 1. So it's basically a sphere with center 0, 0, 0 and a radius of 1. But based off this inequality, it's basically saying that you're considering all points that are greater than or equal to 1. So that's going to encapsulate everything outside of this sphere. So this inequality is actually everything outside of the sphere, right? Now let's look at the other part of the inequality. So that's the left-hand side. So that's this part of the inequality. Yeah. So now let's look at the right side of the inequality. Let me use blue. Let's look at this part of the inequality. So it's going to be something like x squared, or it is going to be x squared plus y squared plus z squared is going to be less than or equal to 64, right? So again, I will start by drawing this out, what this sphere basically looks like. So that is basically going to be a sphere. Oh, wait, let me specify over here that this has a radius of 1, right? Because the square root of 1 is basically just 1. And so over here, we have a sphere. So if you can draw it correctly. Okay, that looks somewhat like a sphere. That looks, okay, yeah, that's a sphere with a radius of 8. And that's just because the formula of a sphere, this is going to look something like x minus 0 squared plus y minus 0 squared plus z minus 0 squared. It's going to be less than or equal to 64. Okay. All right. And again, based off that, my center is also going to be at 0, 0, 0. Okay. So, but now we look at this inequality right here, and we notice that this actually has a less than or equal to 64. So instead of everything outside of the sphere, like the first case, and we have greater than or equal to 1, we have everything inside of this sphere. So that's going to be represented by this shaded region. So everything encapsulated inside the sphere. Okay. So now splitting into two pieces, let's try to combine them into one. Okay, so Let me draw a new whiteboard. Okay, I'm just gonna leave this up there. And let me write down my equation. So we have 1 is less than or equal to x squared plus y squared plus z squared less than or equal to 64, right? So again, so we basically have one inner circle with a radius of 1, right? I'm just going to specify that center is, let me erase that for now. I'll include this later. Yeah. So have that right there. Radius of 1 of a sphere. And we have another circle with the same center, or another sphere with the same center. Okay, let's see if I can draw this out nicely. So, yeah, as you might have noticed, I am not that great at drawing diagrams. So something like that. But instead of radius of 1, we have a radius of 8 in this case. So from this inequality, these two inequalities, the first part, again, going back to this slide right here, is so for r is equal to 1, we have everything outside of that inner sphere, basically. So we have this sphere and everything outside is going to be represented by, let me just use red. So red is going to be everything outside of the inner sphere. And then for the other inequality, where we have a radius of 8, it's going to be everything encapsulated inside of the sphere. So let me use blue to represent that shaded region. Okay. And as you can see, the only area or the volume that kind of intersects between the two different inequalities is going to be, let me erase this. Oh. Is going to be, oh no, give me a minute. Is, oh, okay, there we go. Is going to be this volume. Okay, so representing this equation in R3 is roughly going to be this in R3 is going to be this solid region in space. Okay, so that kind of encapsulates all the key topics for 12.1. The biggest thing to note is the context of your equation or whatever question you're dealing with. So in this case, we're doing it in R3, right? Not in R2. Okay, so one thing to remember. And so, yeah, I won't go over too much regarding the equations of spheres, as in like finding its center and finding its radius, because I think in recitation yesterday, Dom went over, yeah, finding equations of spheres and like given what, 2 endpoints, right, of a sphere. So I won't be covering that. So I guess you can refer to recitation week 1, number 1 for those questions. Okay. All right, so let's go on to 12.2 now. Whiteboard. All right, any questions so far? All right, perfect. Okay, so let's see, 12.2. 12.2 is the introduction to vectors. Okay. I'll be emphasizing more on 12.3 and 4 because that's more of a kind of the introductory application of vectors. So with 12.2 in vectors, the biggest thing to note is the idea of vectors versus scalars. Okay, this is very important in 12.2, distinguishing between the two, right? So scalar basically just has a magnitude, so something like a length, right? While vectors have both a length or magnitude and a direction. Okay, it's very important, not just in chapter 12 to distinguish between the two, but throughout the whole of Math 230 to 31. Okay, so this is very important for 12.2. And so, yeah, so let's see. So I won't be covering too much about the operation. So let's say you're given a vector. Let's say you're given a point of, okay, let me start a new whiteboard. Let's say you're given 2 points. Let's say we have point A and 0, 1, 0, and you have point B at 1, 2, and 3, right? And then we're supposed to find the vector AB, and let's try also find the vector of BA. Okay, yeah, I'll be representing my vectors in this format where you have, yeah, 2 points with a arrow, kind of like, yeah, a half arrow on top. All right, so in order to find the vector of AB, you start off with the second point. So if I were to plot it out, so let's say A is over here, and let's say B is over there. All right, so AB is gonna look like this vector, this black vector, where the head of the vector is gonna be at B and the tail of the vector is gonna be at A. So what you do is always take the points from the point at the head and subtract it with its respective components in point A or in the tail. So in this case, you have 1 minus 0 for the x component, you have 2 minus 1 for the y component, and you have 3 minus 0 for the z component. So that vector is going to be 1, 1, 3. All right. And now let's look at B to A. So instead, I'm going to use red to represent this. So that's going to be, you know, A to B, and then this red vector going the other way is going to represent B to A. Okay. So again, same idea. What you want to do is take, so let me just use red to represent that. You want to take the points at the head. So in this case, the point at the head of the vector is going to be at A. So that's going to be 0. And then that's going to subtract by 1, comma, 1 minus 2, which is the y component, and the z component is going to look something like 0 minus 3. So that's going to look something like -1, comma, -1, comma, -3. Okay. So before we move on, there are a couple of key things which I want to discuss. So one thing that Joe brought up is also distinguishing between a point and a vector. Okay, so points are usually written where you have parentheses for, yeah, so sorry, let me just erase this. Yeah, where you have parentheses on the sides of each respective component. All right, so these are kind of coordinates. While vectors are not necessarily a parentheses because it's not a coordinate, it's the distance between 2 points, right? So in this case, it's the displacement vector, let's say from A to B, right? So that's the distance between B and A. And so we're going to use less than and a greater than sign to distinguish between a point and a vector. Okay. All right. And then another thing to note is this idea of, okay, so hold up, okay. So yeah, so for AB, we have the vector pointing from A to B, and for BA, we have the vector from pointing from B to A, right? Now, there isn't too much of a difference between two except for its direction, right? As I mentioned before, vectors have both a length and magnitude and a direction. So with two vectors pointing in the exactly the opposite way, it's basically gonna be, so we can write it down as AB is gonna equal to the same thing as -B of A. Okay. So having the same magnitude, we just have the opposite direction, or exactly opposite direction. So we can also represent that by this right here. Okay. So yeah, I won't go into too much of the operations. Like you guys covered vector addition, scalar multiples, and this idea of the zero vector. I'll leave that for you guys to review looking over the lecture videos. Okay. But the last thing I want to bring up in 12.2 is this idea of normalizing a vector, because you'll be seeing this well, this will be helpful in a lot of different cases, but you see kind of a glimpse of what it can be used for in the cross product or in the dot product when you're dealing with projections. Okay. So for 12.2 for normalizing vectors, it's basically this idea of making, so let's say we have this vector of, let's say we have a vector A with the components of 1, 2, 3. Okay, so we have this vector right here, vector A. So normalizing vector basically is taking this vector of A and utilizing this vector, we're basically making it to a unit vector of length 1 with the same exact direction of A. So as we covered in, or as Joe and Dom covered in lecture and recitation, this idea of a unit vector is basically a vector with a size of 1. So something like, let's say, vector B is equal to 1, 0, 0, and calculating the magnitude or the length of a vector is basically using using the distance formula. So like taking the square root of 1 squared plus 0 squared plus 0 squared, which is going to be the same thing as 1, right? That's the magnitude of this vector. So whenever you have a magnitude of 1, that basically represents a unit vector. So in this case, what we notice is that, so I'm just going to clear this up. All right. So in this case right here, what we notice is that this has a magnitude of 1 squared plus 2 squared plus 3 squared. So that's square root of 4, 9, 13, 14, right? So now normalizing a vector is basically treating the same vector in the same direction, but just manipulating so it has a length or a magnitude of 1. So what we can do is we can take that vector A, and we divide it by the magnitude of A, which is represented as the absolute value of a vector. Okay. So in this case, that is going to be the same thing as square root of 1 over square root of 14 multiplied by 1 by the vector 1, 2, and 3, right? And you can double check that the magnitude of this is going to be equal to 1 by just doing a scalar multiple of this to the vector and taking its, or finding its magnitude from there. So if I were to represent this as 1 over square root of 14, 2 over square root of 14, and 3 over square root of 14, this vector is gonna have a magnitude of 1. And yeah, I think that's it. Oh, actually one more thing. All right, so yeah, that's basically kind of the gist of 12.2. And one more thing that they introduce, or let me erase this real quick. Let me just start a new whiteboard. All right, so one more thing they introduce in 12.2 is kind of another form in representing a vector. So let's say we have the vector v, and that is going to be represented by 1, 2, 3. Okay, let's just use same vector. This can also be represented as I hat plus 2j hat plus 3k hat. If you guys have taken physics before, this might look somewhat familiar, where I, j, k, basically this represents the x component, this represents the y component, and k represents the z component of a vector. All right, and this is classified as the basis vector form of, a vector. So either form of representing a vector should work. And again, since you're taking this online, I don't know, I haven't taken an online course before, so I don't know how they mark notation and all of that. Okay, and that's probably best to ask the instructors, Joe and Don. Okay. All right, so that's 12.2. Now let's get into 12.3. Oh, okay, so now is the introduction to the dot product. Okay. And again, just like Joe was saying in Tuesday's lecture, don't consider this as multiplications of vectors. Okay. And yeah, he explains this a bit more deliberately in the lecture. So feel free to look over those lecture videos. All right, so let's start off with the definition of a dot product. So let's say we have a vector A. So let me just start off with writing down what we have. So let's say we have two vectors, one vector A. Oh, let's say 1, 0. Let's see what I have. Let's say I have 1, 9, 10. Okay, 1, 9, 10. And let's say that I have a second vector B as, let's see, what do I have? 2, 7, 3. Okay. All right. So yeah, we basically have two vectors. So in regards to a dot product, what you always want to consider is that you always want two inputs that are vectors, which will which will have one output of a scalar quantity. Okay. And this is why it is, again, very important to distinguish between a scalar quantity versus a vector quantity. Okay. So yeah, for dot products, yeah, you're gonna label this as, so let's say we're taking the dot product of A dot B, and that's the same thing as A1 times B1 plus A2 times B2 plus A3 times B3. And then that is also equal to the magnitude of A times the magnitude of B cosine theta. Okay, so we'll look into this more, more deliberately. So yeah, so let me start off by looking at this. All right, so again, as you know, the output of a dot product should become a scalar quantity, and just shown here, right? These are just all scalar. This is going to be a scalar quantity with no direction, right? So if we're just taking the dot product of these two vectors, it's gonna look something like, so yeah, let me just label this clearly. So that's A1, that's A2, that's A3, that's B1, that's B2, and that's B3. Okay. All right, so for A dot B, again, that's gonna be 1 multiplied by 2 plus 9 multiplied by 7 plus A3 is gonna be, what's that, 10? Yeah, multiplied by 3. Okay, so it's gonna be something like 2 plus 16 plus 30. Okay, that's gonna be big numbers. That's gonna be 48. All right, now let's look at this really quickly. So this, again, so for the dot product, as Joe mentioned in Tuesday's lecture, it's also kind of how aligned two vectors are to each other, right? So if I should draw this out, if I were to draw, give me a minute, move this around a bit. Okay. Okay. So if I were to draw two vectors, right? Let's say in this case, I have vector A pointing this way, and let's say I have vector B pointing this way. Okay. All right. Yeah. All right. So, and this is going to represent theta for now. Okay, I'll explain that a bit more. So as Joe was saying, yeah, how aligned these two vectors are to each other. Okay, and this follows the law of cosines. You can refer to the textbook for the formal proof for it, but I won't be discussing that today. And so when we look at this, the scalar multiple or the scalar result of 48, what does that mean? That is basically also equal to the magnitude of A multiplied by the magnitude of B cosine theta. All right, and this theta represents this theta right here in between the two vectors. Okay, so let me use red. I'll use red for theta. Okay, cos theta right there. All right, so we have that. All right. So now cos theta, we're only going to be considering that, as Joe is saying, in between 0, theta and pi, right, in radians. So so we have 3 different cases, basically. The first case is going to be when theta is in between 0. It's going to be less than or equal to. Less than or equal to 0, and it's going to be less than pi over 2. We have the second case where theta is equal to pi over 2, and we have the third case where theta is in between pi over 2 and pi, right? So when you have a cosine of an angle between 0 and pi over 2, that's just going to result in a positive value, right? Because if you refer back to the graph of a cosine, right, it's going to look something, or that's how I look at it. I normally refer back to the graphs of the cosine, or trig functions. So that's going to look something like that, right? So from 0 to pi over 2, let me just, 0 to pi over 2 is going to be a positive value. From at pi over 2 is going to be 0. And in between pi over 2, or sorry, we have pi over 2 and pi, it's going to be a negative value. All right. So based off this value of 48, we know that it's a positive value. So this has to be an acute angle. So these two vectors will basically form an acute angle, right? Because an acute angle is anything less than 90 degrees, right? So this basically proves that you have an acute angle between the two vectors. All right, one thing to note about the dot product is that whenever you have two vectors, or what is key is that whenever you have two vectors perpendicular, or another way of saying it is orthogonal to each other, is that you will have a dot product that is gonna be equal to 0, okay? So that's something worth mentioning, or worth noting, okay? All right, and yeah, that's the basic idea of dot products. All right, any questions? No? All right, perfect. Okay. Oh, and one last thing I want to cover from 12.3 is this idea of projections. I know Joe and Dom have covered it, but I want to reiterate this idea of projections. So let's start off. So there are two different projections that you guys covered. One is a scalar projection, and the other one is a vector projection. Okay, so scalar projection and vector projection. Okay. Is this how we want to do it? No. Let's just do projections. And let's say we're given again let's start off with a simple example of a vector in XY plane. So let's say we have V is equal to 1, 3. Okay, just has an X and Y component. All right, so the idea, I just want to reiterate the idea of projections first. All right, so let's say we have a vector that is that has an X distance of 1 and a Y distance of 3. So let's say it starts off at the origin and it goes to that point right there. Okay, let's say this is our vector. Okay. So for the scalar projection, which is denoted as comp of B onto A. Okay, so that's a scalar projection. So for scalar projection, so let's say in this case we're trying to find what comp of let's say V. Yeah, let's label this as V is onto the x-axis. So I'm just going to label that as I, right? Because I is the x-axis basically for the basis vector form of a vector. So let me say I want to try find what comp V onto I is. So that's basically the scalar value of the x component. So that's going to represent this value right here, basically. So the scalar value there. Okay, it's not going to be a vector. It's going to be a scalar quantity. So from this projection, we know that, so let me just draw a, why not? There, and then that is theta, right? Let me just label that. So I'm just going to create this right triangle. Let me say that's theta. And you guys have probably seen this if you guys have taken physics before. So in order to find the x component, we just basically take the cosine, right? The cosine of theta is going to equal what? Cosine theta is going to equal, use black. Okay, cosine theta is going to equal to this, let me label this as x, the x component all over that magnitude of v, right? And so that is why x is going to equal to v cosine theta. And so if we're trying to find the scalar projection of v onto I, or the x-axis, that's basically going to be the magnitude of v cosine theta, as you have probably seen before. And by using the product rule in substitution for this cosine theta, that's going to be the same thing as, what is it, as I dot b, yes, I dot v, sorry, I dot v all over to the magnitude of I and the magnitude of v. Right, so that's going to be equal to I dot v all over I. Okay, remember this is not a this is a dot product between the two vectors. All right, and so the other idea is this idea of so let me start a new one. Bird. This idea of vector projections. All right, so vector projections is sort of similar. But it's taking into account also the kind of the direction. All right, so for vector projection, it's basically going to be okay. So actually, yeah, let me use an example in R3 to introduce this new idea of vector projections. I'm sorry, let me erase this. All right, so yeah, so I'll introduce vector projections in a bit, but yeah, in terms of these projections, it might not always be the case where
Wait, I have a question.
Yeah, what's up?
So right at the very last step, shouldn't it be magnitude of I underneath instead of
yeah.
Okay, thank you.
That should be magnitude of I.
Okay, thank you.
All right. So that is it for, okay. So yeah, let me get on to, so yeah, as Joe was saying on Monday, on Tuesday with projections, it might not always be the case where you're representing kind of like the projections on an X or Y axis, but rather on another vector, right? So let's say we take the two examples we covered before, where we have A is equal to 1, 9, 10. And we have B is equal to 2, 7, 3, right? So let's say we're trying to project, or we're trying to find what, so let's say, let me just draw it out. So let's say I have B going this way, and I have A going this way, okay? So these two vectors, basically. All right, so let's say I'm trying to project, I'm trying to project B onto A, right? And I'm trying to find the scalar projector first. So going back to that idea, I'm just basically trying to take into account the scalar quantity of the x component of B, right? Or not the x component, rather the component that is projected onto the vector A. So going back to that formula, we have comp of B onto A, since I'm trying to find a projection on A, which is the same thing as A dot B all over the magnitude of A, okay? And this is basically the same thing we covered here with the scalar projection. So this, again, I'm just gonna highlight this. this is going to represent the scalar quantity, right? Again, it's a scalar quantity of the component that mirrors A, I guess, from the B vector. Okay, so scalar quantity of of the projection of B onto A. Okay, so this is scalar quantity, and now let's look at the vector projection. Okay, so this is scalar projection, and now let's cover this idea of vector projections. All right, so vector projection. All right, so with scalar projection, the scalar quantity, vector projection is basically you're trying to find this vector right there. So if I have to label this in red, you're basically trying to find that vector right there. Okay, and that is why you're gonna tie in the idea of normalizing vectors in this case. Okay, because what we can do is we can normalize A, right? And in normalizing A, you basically get a length or a unit vector that is in the same, or it basically follows the same direction as A. So by normalizing A, we get A all over the magnitude of A, right? Which is gonna be a vector with unit length of 1. But the most important thing to note is that this has the same direction as A. And that's basically what you want first. So that's how I look into it. And so we basically covered the direction of A, of this vector right here. So I'm gonna just label this as, X. Okay, let's just label this vector X. All right, so for the direction of X, we basically said we have the direction of A, which is just gonna be A all over plus the value of A, or the magnitude of A, okay? Now, another thing to consider is your magnitude. Okay, what is the magnitude gonna be? Anyone have any guesses? No? All right, so what is it? It's basically gonna be the scalar quantity that you calculated over here. This magnitude is gonna relate to this right here. And that's why when you look at the formula for the vector projection, or like when you look at, the projection of, or vector projection of B onto A, it's gonna be the same thing as comp B onto A multiplied by the vector A divided by the magnitude of A, okay? Okay, and the reason why is because this basically represents the magnitude of that vector. So multiplying, again, going back to scalar multiplication of vectors, multiplying that scalar quantity with that vector right there, that unit vector in the same direction of A, will give you the vector X, okay? And yeah, all right, so let's actually try and solve it using these two vectors. Let's find what the projections are, both scalar and vector, okay? So again, using these same vectors, so we have A, how much time do we have? We get 12 minutes, okay, got some time. 1, 9, 10, and we have B is equal to 2, 7, 3. All right, so let's start off with the scalar projection of B onto A, which is the same thing as A dot B all over the magnitude of A. Okay, so again, I'll start off with A dot B, which is going to be the same thing as 2 plus, what is that, 7 times 9, which is 63 plus 30. All right, all over the magnitude of A, which is going to be what? Square root of, I'll just write it here actually. So that's going to be the square root of 1 squared plus 81 plus 100. Okay. So that's going to be what? 93, 95, all over the square root of 182. Okay. Again, you can simplify that, but I won't just for this. And then now let's try to find the projection of B onto, or the vector projection of B onto A. So it's just going to be 95 all over square root 182 multiplied by normalizing the A vector, or the vector that you're trying to project it onto. So in this case, you're trying to project B onto A, right? So we're just basically normalizing the vector A. Okay, so that's gonna equal, let me use parentheses right there. So that's gonna equal what? Vector A all over the magnitude of A, which we calculated was square root of 182. So that's 95 all over square root of 182. Okay. All right, and yeah, I think that's it. So you can simplify this as 95 over 182, multiply the scalar multiplication with vector A. Right, so that's the vector projection of B onto A. All right, so that is it for 12.3. Now the last topic we can cover today is 12.4, is this idea of cross product. All right, so let me start off with the definition again. So let's say we're using, let's use two different vectors this time. Okay, yeah, let's use different vectors this time. Say A is 1, 0, 3, and let's say B is equal to, what is it, 2, 3, and 7. All right. So in terms of the cross product, it's going to be two inputs of vectors again, but the only difference is it's going to output a vector 2. Okay. So this will not output a scalar quantity like in dot product. It will actually output a vector quantity. Okay. So I won't go through the kind of like the mechanics of how to find a cross product. You guys covered it already in recitation and lecture, so I'll just be going through this example, right? So again, let me just write down the definition. A cross B is going to be the same thing as the, what is it? The magnitude of A, the magnitude of B, sine theta. And also to calculate A cross B, you're basically taking the 3 by 3 determinant of these two vectors. Okay, so that's one way of solving A cross B. Another way of solving A cross B is utilizing this right here. This 3 by 3 determinant JK of 1, 0, 3 and what is it, 2, 3, 7. Okay. So again, as you guys covered in class, when you're taking the first component, so let's start off with I. So what you do is you kind of just block, let's see what I can use. So if you're looking at the I component, let me label this as red. Looking at the I component, you just kind of get rid of everything in the row and everything in the column. And you look at this 2 by 2 quadrant right here, and then take that determinant of the matrix. All right, so it's gonna be something like, oh wait, sorry. Okay, that's gonna be determinant of 0, 3, 3, 7. And then it's gonna be subtracted by J with the determinant of 1, 2, 3, 7. Remember, it always alternates, right? And plus the K hat, or the K component of 1, 2, 0, and 3. All right. So basically, that's going to be your new vector. So again, this is in basis vector form. You guys can use component vector. Either way works. Okay. So let's say we find this. We've actually calculated this out. Let's see. This is going to be nice. Okay. So it's going to be 9 minus 7. That's going to be 2i minus j of, what is that? 7 minus 6. That's going to be 1. So I'm just going to leave it at that. And then plus k hat of 3 minus 2, right? That's going to be 1, 2. So that's going to be your vector of A cross B. So what does this vector or this result actually represent? This is actually another vector. So like if I have to draw out A this way, this vector A, and you're crossing it with that vector B, that A cross B is gonna be this other vector as covered in class, right? It's gonna be orthogonal or perpendicular to both B and A. So something to note is that A cross B is perpendicular to A, and A cross B is also perpendicular to B. Okay, and this, another way of representing this is that if you take the cross product of the two, all right, if you take the cross product, oh, not the cross product, sorry, the dot product of the two, that should give you a 0, right? And same thing goes with this one. All right, so yeah, again, that is basically the vector. So in this case, we calculated it was 2i minus j plus k. So that's going to represent 2i minus j plus k hat, right? All right, now there is another thing to note about cross products. So as I mentioned, you created basically another vector that is orthogonal to both B and A. But what you notice is that there are two directions where A and B, or the new vector, can be orthogonal to both A and B. One is upwards and the other is down, right? Wouldn't this also be valid? Question mark? Right? Because if you draw a vector downwards, that would also be orthogonal to both A and B. But that is actually not true. Okay. And the reason why is whenever you're considering creating that new vector, although it's orthogonal, it also follows the right-hand rule. And I think you guys covered this in Tuesday's lecture. So how I think about this is, so let's say we have A going this way, right? So what I do with the right-hand rule is I follow my fingers to A. So since A is going this way, I go this way. And then I basically curl towards B. And wherever my thumb points towards, that's where my resultant vector is going to point towards. So in this case, A is going to point this way. It's going to curl towards B, and then it's going to go upwards. Another thing to point about this method is that your fingers should always curl towards your palm. Okay. So you can't so let's say we have A going this way, right? If you have your fingers going A this way, it can be going this way or this way, right? Because I just said my fingers move towards A, moves along A. So if, hold up. Okay, I see the chat box now. How did you get K? Shouldn't it be 3K? All right, hold on, give me a minute. So, okay, there was a question. So how did you get K? Shouldn't it be 3K? 3 minus 0, I can't figure out how to, oh, okay. So let's see. Let's go back here before we go on. Ah, okay. Oh, nice. All right, thank you. Yep. Yeah, so I made a mistake somewhere here. So finding the determinant is actually, yeah, it's not going to be K, but it's going to be 3K. All right, nice catch. Okay, so that's going to be 3K. Whoa.
I believe the I vector is also supposed to be negative 9i.
Yeah, it's going to be negative 9. That is my bad. Thank you. Yeah, negative 9. Let's see. Yeah, so that's going to be negative 9a. And let me just double check this one. 7 minus 6, right? Not, yeah, that's going to be 0. That's going to be 9. That was my bad. I think I might have added these for some reason. Okay, so yeah, going back to the right-hand rule, again, A moves along with, the first vector you're doing your cross product with goes with your fingers and it curls towards the second vector. Okay, all right, and you always want to go towards your palm, never away from your palm, because like you can't, yeah, that's probably a great way to get carpal tunnel or something. All right, so yeah, all right, so yeah, okay, that's cross products. And another thing to note is the direction of your resultant vector, because that should come up in the homework. So yeah, I think that's it. Okay, and oh yeah, one more thing to note is this idea of a parallelogram. So going back to the definition of the cross product, this is one way of solving it, right? But there's also a second representation. So let me just label this as 1. Let me label this as 2. All right. A cross B is also synonymous to the magnitude of A multiplied by the magnitude of B multiplied by sine theta. What is this? Let me label this. Let me let's use blue. Okay. So, oh no, that doesn't make any difference. All right, let's use green. Yeah, this is green. All right, sine theta. Say, let's label that angle theta green. That angle is actually going to be in between these two vectors. Okay, it's going to be theta. All right, so if I look at A and B, because if I redraw that, let's go back to black. So A is going this way, and then B is going this way. Again, they're vectors, so I'm just gonna write down that is gonna be theta. Okay. So another question. So in other than finding the finding what A cross B is, finding the direction of the new vector, another question they might ask is, as I think you guys have covered before in recitation and lecture with either Joe or Dom, is this idea of finding the area of the parallelogram, all right, created by these two vectors. Okay, so covered in lecture, it's gonna be A cross B, or the magnitude of A cross B. It's gonna be the same thing as your area of the parallelogram. Okay, that's one thing to note. This new area of the parallelogram basically is going to be the same thing as the magnitude, right? The magnitude of A cross B. Okay. All right. And yeah, just to show you why, if I were to, let me just draw this out. If I draw a right triangle right there, what is it? B, what is it? Yeah. So B sine theta, right, is going to represent this side right here. And if you multiply that with A, that's going to give you the area of the parallelogram. And that's the same thing as the cross product. Okay. And yeah, you guys can look, I think Joe definitely mentioned this Tuesday's lecture. So definitely, if you want to go over that again, yeah, refer back to a lecture on Tuesday. All right, so yeah, how do we find the magnitude or the area of the parallelogram? Basically, find the cross product as we found, which was this, which was negative 9i minus j plus 3k, right? So negative 9i minus j plus 3k, minus j plus 3k, right? And then just like how you would normally find the magnitude of a vector, you just find this magnitude right here, which is going to be the square root of 81 plus 1 plus 9. Right, and that's the same thing as, what is that? 89, 90, square root of 90. Right, which is what, 3 square root 10, which is the same thing as, yeah, I don't think I can simplify that. All right, and yeah, that is basically it for, yeah, for 12.4. Oh, and one last thing is this, yeah, you guys briefly covered triple scalar product, which is basically A dot B cross C, right? So given three vectors, yeah, the application of this is finding the volume of a parallelepiped. So if you have something like B right here, let's say C right there, and let's say A right there, you can find the volume of the parallelepiped. So if you extend this out, all right. Yeah, I don't think. Yeah, but yeah, you can refer back to the, I won't be going over this too much, but yeah, this is kind of the idea of triple scalar product, right? So taking the, you can, so if we, let me introduce three vectors. Let's look at three vectors. So I should go over one example. Let's go 1, 2, and 3. let's go B as -1, 1, and 2, and C as 2, 1, 4, right? So one way of doing this is, yeah, you can take the cross product of B and C and then taking the dot product of that. That is valid, but another way of doing this is actually, again, following that 3 by 3 determinant. So 1, 2, 3, -1, 1, 2, and 2, 1, 4. So basically finding the determinant of a 3 by 3 matrix. Okay. So that's going to be something like 1, right? +1 multiplied by the determinant of 1, 2, 1, 4 minus a 2, the determinant of -1, 2, 2, 4, and lastly adding 3 multiplied by the determinant of -1, 1, 2, 1. Okay, and that's this new idea of a triple scalar product. Okay. All right, and yeah, I think that is it for today's session. We are just about out of time. Any questions so far? Or any questions in general about GSG? No? All right, perfect. Oh yeah, if you guys weren't here in the beginning of the session, please type in your PSU ID on the chat box. And another announcement I'll probably make in Piazza is, or the announcement regarding GSG is that, again, this whole setup is for you guys. So whatever you want me to do during these sessions, feel free to let me know in Piazza, email me, or just, yeah, stop in one of these sessions to let me know what you guys want to cover. All right. Well, all right, I guess that's it. All right, thank you for tuning in. I'll see you next week.